All right, so I'm Thomas. If you don't know me, I'm the Hardware Outreach Officer, and today I'm going to be giving an intro on hardware security. So what is hardware security? Well, apart from disassembling toasters, it's basically attacking and defending the many components of computer systems and electronic systems. So one of the many ways we can do this is through fault injection, where we use some technique to cause a system to do something that wasn't initially intended by the creator or developers. This can vary from anything from hitting it with a hammer, making it do something, to messing with like the insides of it to cause it to break. So one technique is clock glitching. And what a clock is, it's like a square wave. It just goes up, goes down at a set frequency. And this helps keep all the components on a computer in sync so that they can do operations together to cause something to happen. So like say when you add, it's going to add on the rising edge of the clock and it's going to do that so all the other components in the computer will know when their information's ready to be added and when the information's ready to be read. So when the computer's trying to do that, we can introduce a clock glitch, which is like that little bump right there, the small one, where we change the frequency and make it really fast, faster than the hardware is expecting, and we can skip instructions in a program or cause the program to misbehave. That's pretty cool. So on the ATmega 328P, which is a microcontroller, it's basically like a mini computer. This is the block diagram. And we can see from the flash program memory, that's where your program is with all the instructions. It's going to read in that instruction to the instruction register, and then it's going to decode that instruction. Well, if we introduce that clock glitch while it's decoding that instruction, we can cause it to misbehave and possibly skip an instruction. So this is useful, say if your program's like comparing a password, and then it reaches a certain point in the program where it's like, oh, this password's wrong, I'm going to go do something. Well, on that part of the program, if you were to introduce that glitch, you can skip that instruction. Instead of going somewhere else in the program, you would go as if the password passed. Another way to do something like this is to do power glitching, where you momentarily drop the voltage. And the voltage is like the amount of energy you're giving to the computer. So what you'll do is you'll have the power at a constant level. And then when you want to skip that instruction, you drop it to 0 really quick and then bring it back up. And you can achieve the same effect as the clock glitching, where you skip instructions or other operations. This is a graph of the power being constant and then being dropped really quick. It jumps around a lot because hardware is complex. But basically, it's a constant thing, and then you drop it, and then you bring it back up. So let's talk a little bit about side channel attacks. And that's where information is leaked from a system by the implementation of the system. So one example of this would be, say you're taking a math test, and you know that the test is going to be one problem, and you know it's going to be one of the two problems that was on the review. And you know that one problem requires a calculator and one doesn't. So, and you can only memorize one because memorizing 2 questions is too hard. So you go to the section before you, they're taking the test, you're outside, and you put your ear up to the door, and you hear people clicking on a calculator. And because you know that they're clicking on a calculator, you know that they're doing the problem that requires a calculator. And from that, you're able to figure out that the problem on the test is the one that requires a calculator without ever seeing the test or being told that the problem is the one from the calculator. So one side channel attack is a timing attack. And that's where the information that's being leaked is the amount of time an operation takes. So if we look at this piece of code, what this code does, it's going to take in a password, compare the length. If that passes, it's going to go through each character and compare it. And if that passes, it'll print good. If it doesn't, if one of the characters don't match, or the lengths don't match, it's going to print bad and exit. Now this seems like it would check the password pretty well, and that you wouldn't be able to figure out what's going on if you weren't able to see what's running in the code. But say we were to supply a password like A, it would fail quickly because the lengths are different. But if you were to say supply a password that's the same length as Hunter2, it would take a little longer because it wouldn't exit immediately. It would go into that for loop. So using that time difference, you can figure out, hey, the password is 1, 2, 3, 4, 5, 6, 7 characters long. And so you'd be able to figure out that it's 7 characters long, and then you'd be able to get into the for loop and do some operations. So it's going to go character by character. So say you guess A. So through the first time through the loop, it's going to see that those characters don't match, and it's going to exit really quickly. But say your first character was H. It's going to pass that for loop once, and then go back to it again. And so it'll do the loop twice and then exit, which is going to take a little bit more time. And you can keep building that up and going character by character until you have the whole password without actually trying all possible combinations. And that is because you're able to figure out how long it takes to compare the password. And the solution to this is to make all operations take the same amount of time. So instead of exiting when there's a bad character, you can just keep looping through the characters even though you know it's wrong. And this will make every password check the same amount of time, and you won't be able to figure out what's going on based on the time. Also, if you have any questions, just feel free to ask. Another side channel attack is power analysis. And this is where you measure the power usage of a system. And from that, you're able to figure out what's going on in that system. For example, RSA is an encryption algorithm. And in RSA, when you implement RSA, there's some hardware optimizations where when you're encrypting something from the private key, if the bit is a 1, you'll do a square and multiply. And if the bit is a 0, you'll just multiply. And from this, if you look at the power usage, the square is going to take a little bit more power than the square and multiply is going to take a little bit more power than just the square alone, the square operation. So what you can do is you can record the power over time, and you'll see that it'll jump up for a little bit and then jump up again, but the amount of power is going to be different. So based on how much power each little spike uses, you're able to figure out if it was a square and multiply or a square, which allows you to go back and figure out if it was like a 1 or a 0, a 1 or a 0, and then recover the private key of the RSA. And the solution to power analysis is to add noise, which is basically do random operations in the background so that you're not able to attribute certain power usage to an operation. And also reduce signal, so maybe make all operations take the same amount of power, so you can't differentiate between what the input is and how the input affects power usage. Another type of side channel is data remnants, and that's where data is left on a system even after it's been powered off or something like that. So that is some RAM, and RAM is the component on your computer where the memory of your operating, where your operating system and all the programs that run on your computer is loaded into. And there's a thing called a cold boot attack, where if you freeze the RAM, it'll stay on the RAM longer than normal when you shut down. So what you can do is, say you just turned off your computer, normally you'd expect that memory to be gone, but if you were to spray it with, say, like a canned air type thing and you turn it upside down and you freeze the RAM, the charge on the RAM is going to retain longer, so you'll be able to take it out, put it in a new machine, and then read all the RAM read what the computer was doing before the shutdown. Yeah?
How viable is that? Like, has that attack been executed and shown to work? Because it sounds like it would be very, very hard.
It's been shown in research papers. Yeah.
Yes.
Cool. So our next side channel is Meltdown Inspector. And what these vulnerabilities allow is, Meltdown allows you to read all memory in the computer, so the operating system memory and every other program's memory. Inspector allows you to read all memory of another process. And the way this works is that, so what your computer does is it sequentially executes instructions, but some instructions are longer than the others. So what your computer will do is, while a long instruction is happening, it's going to go down and execute smaller instructions while it's still waiting for that other one. So say this instruction were to fail normally, and it would fail because it's accessing memory it's not allowed. The instructions below it normally wouldn't get executed. But your computer is trying to be fast, so while it's waiting on that top instruction, it's going to go down and execute the other instructions. And then it's going to see that this one fails, and it's just going to throw away the operations. But as a side effect of running those other executions, those other instructions, it causes something called a CPU cache, where if those other instructions try to load memory that hasn't been accessed in a while, it will load that into the CPU, the CPU's cache, which is like a smaller portion of memory that's faster than your RAM. And because of that CPU cache, it's gonna, after the program fails, you can try to access that memory again, and based on how long it takes, you can figure out if the memory was cached or not, which you can use that to rebuild what the memory is at a place you weren't supposed to be able to. And Inspector is similar, except that it relies on branch prediction, where what branch prediction is, so say there's like an if statement in your program, it's going to go down one branch if the condition fails, and it's going to go down the other if it passes. But what your computer is going to do to go fast is, while it's checking that condition, it's going to choose the most likely branch, the most likely to execute branch, and then it's going to execute those instructions while it's waiting for the condition. So if the condition happens, if the condition is being checked, and then it goes down this way. So the condition's being checked, and your computer predicts it's going to go down this branch. It's going to execute that. But after the condition finishes, it's going to go down the other branch. So what can happen is, while it predicted that other branch, it's going to load some, it's going to cause a CPU cache again, which as in Meltdown, you can use that to rebuild what is going on. And these vulnerabilities are unique in that the vulnerability is in the hardware, but you can trigger it from the software and use it from the software. So before we get into our next side channel, I wanted to talk a little about what radio is. And radio is really just electromagnetic waves. And all wireless devices use some form of radio, and that's how they communicate. And all wired devices use some form of radio. Because when you run a current through a wire, it creates an electric field which can be interpreted as a radio wave. So our next side channel is electromagnetic attacks. And that is basically some electric field or something like that is being emitted by some electrical component. So like this HDMI cable right now is creating a field which can be interpreted as a radio wave. We'll get a little bit more into this, but the solution to preventing this is to like shield cables so the field emitted is weakened, increase noise by maybe putting a jammer that creates some radio wave at the same frequency that the cable is emitting, or decrease signal by decreasing the amount of field it's emitting. So Tempest is an NSA project that focuses on side channel attacks and how to defend and how to attack. So some of the some of the research that has been shown is that you can actually recover like a computer screen from a couple rooms away. So this is a laptop screen that was recovered from 10 meters away through 3 or 4 plasterboard walls. And this was, I'd like to note that this was in 2006. So based on how things have improved, I'm pretty sure computer screens can be recovered from a lot further. This one is more recent, but what's going on here is that we have a computer screen right here, a microphone on top, and then some equipment on the left, which is going to interpret that signal from the microphone. And what they've actually shown is that you can recreate what's happening on the screen through a microphone near that screen. So say you put your phone by your screen and like no one can see your screen, right? Well, your phone you might be like in a call, and through like sounds that they can capture from that, you can recreate what's being displayed on the screen. Yeah?
Is it realistic that your phone would pick up the audio quality necessary to actually do that? Or would it have to be like a really high quality microphone?
So they actually also did it with a Google Home. They placed it right next to the screen.
So
Yeah.
did Google Home awake?
I don't know.
Okay. That would be crazier.
Yeah, so the microphone doesn't need to be that
Okay,
good.
cool.
Mm-hmm.
Do you know what frequency range they're talking about?
I do not. I have the paper if you want to see it after. So how do we attack hardware? So to attack hardware, we first need some hardware. So I brought this. It's a garage door opener. So now that we have the hardware, what do? Well, we have to figure out what the hardware does. Well, you press a button, it sends some signal out to some receiver, and then that receiver interprets the signal and then opens the door. So, what kind of information is on here? Well, upon looking at it, there's a thing called an FCC ID. And what the FCC is the Federal Communications Commission, and they basically manage like all radio waves that are in some product in the US. So if we go to fccid.io, because the FCC's website is super hard to navigate and this website makes it easy, you basically just plug that number in there and you'll get information such as whatever frequency it operates on, external and internal photos, which is useful if you don't actually have the device, but you want to see what it's like inside. Test report where they'll actually record what it's emitting, and a user manual and various information like that. So here's some of the pictures I got from there. That's the external photo. Internal photo, which sometimes they even have the schematics for the circuit inside. And this is the test report, which we'll see more of later on. We see it does a bunch of stuff in the beginning. There's a little gap, and then it does a bunch of other stuff. So before we go more into that, let's talk about what software-defined radio is, or SDR. So normally in like hardware-defined radio, like the radios in your car, it's going to receive some signal on the antenna, pass it to some dedicated hardware that interprets that signal, and then passes it on to your speakers, which plays like music. But in hardware-defined radio, that hardware can't change. It's going to interpret a signal in some encoding and then output it in what it's expected to. But in software-defined radio, it captures that signal. It doesn't do anything to it. It sends it to your computer, and your computer can interpret it however it wants. So this is really useful, say if you're trying to listen to different types of encoded signals. So like AM, you change the amplitude of the wave that corresponds to the signal you're trying to get, and FM, which you change the frequency to correspond to the signal you're trying to get. So if you had like hardware that only works on AM and you try to interpret FM, it's not going to work. It's only going to use the AM. But if you have hardware that's trying to interpret FM and you want to listen to AM, it's not going to happen. But with software-defined radio, you're going to get that raw signal, and then your computer will do whatever it wants with it, so you can switch behind different encodings. The downside to software-defined radio is that it's going to be a bit slower because your computer is going to be interpreting that. So let's capture some waves. So this program right here is connected to this device on, you can't see it, this little silver thing, which is a SDR. And that's connected to this antenna over here. And this device is going to let us select what we want to listen to, and it's going to show us what we're listening to. So right now it's listening on 372.5 megahertz, which is the frequency that the FCC said this thing operates on. So if I click a button, you see that little bump right there? That is the signal of this. So I can keep clicking that. It'll come up. And you can actually listen to like radio stations and stuff on this. It's pretty cool. So what if we were to capture that signal and record it? Well, I went ahead and did that beforehand. And I got that signal up there. And that looks very similar to the FCC report, where it just does a bunch of junk in the beginning, there's a break, and then does some other junk. But if we take a look at the widths of those waves, in the beginning, those are all equal length widths. And then there's a break, and then the widths start to vary. Now, it seems like there's about two widths. There's like a short one and then a long one, or 1 and 0, binary. So it looks like it's sending some kind of binary. But what if we were to replay that same signal from another device? Would the garage door still open? Yes. So that's called a replay attack, where you capture a signal and replay it. So what's pretty cool about this is, say I'm like driving home, and then I open my garage, and then some guy in the bushes is like, with this SDR, he records that signal. Well, at a later time, he could come and replay that signal from some other hardware and get into my garage without actually physically having this little device. So our next topic is the Internet of Things, which is the network of physical devices, vehicles, home appliances, and other embedded systems with electronic software, sensors, actuators, and connectivity, which enables these things to connect, collect, and exchange data. That's a lot of words. Let's talk about what that actually means. It's basically any device that sits in your home and does something without and connected to the internet. And it's not like computers, but like an Amazon Alexa type thing. My personal favorite is a Bluetooth connected toilet, because why wouldn't you want your toilet connected to your phone? And up top, there's a vulnerability report on this, which says that this toilet has a hard-coded Bluetooth pin, which allows any attacker who gets in proximity to trigger physical resource consumption, water or heat, or my favorite, user discomfort. So devices like this are typically rushed to market, and security is an afterthought. So there's tons of devices that are on the internet and aren't well designed for security. And to add to that, most of these devices are only supported for a short amount of time, but they are left on the internet for a long amount of time. So they can go out of date pretty quick, which makes them very vulnerable. Questions? Yeah.
So when you had the thing with the garage door opener,
Yeah.
what would you do if you wanted to do a replay attack, but you didn't know what the person had or what kind of device they had or something like that?
If you didn't know anything about
Anything about it, yeah.
you go and look. You would have to figure out like what they're using to start to try to find a way to attack it. Yeah?
What protections are available for that replay attack?
So you can do things where your code changes every time. Like you can use complicated math that does that. But there's also, if you say like you change the code every use, well, what if I were to press the button out of range of the receiver? How would it know that I'm ahead now? Because I used a code, and you're going to increment that code. So what you can do is, so you're going to increment the code every time you use it. And the receiver's going to increment the code every time it receives it. But if you're out of sync and you go ahead, that's fine with the receiver because you're ahead of what's been played. But what you can do is, if say you jam the signal, and then someone goes to open their garage, and then you record that code, and then they're going to press it again because it didn't work. And you can, you have one code, they pressed it again, and you jam both of them. But now you send the old code, and that receiver's a little bit behind the codes, the code that the transmitter's on, and that gives you a code that is still valid that you can use at a later time. And you can keep, yeah?
Oh, no, finish it.
And you can keep doing that and have free access, yeah?
Free access to the garage.
Yeah.
Are you able to do that level of targeted jamming?
Yes. Well, it depends on the receiver.
Yeah, that's perfect. All right.
It depends on the receiver. So, like, where is it?
Like, basically, could I jam the...
So you see that signal is, let me get the red line to it. Like right there. Well, what if we jam like 2 hertz, like a few hertz above? With a precise enough device, we'd still be able to differentiate between the 2 signals. But the receiver's probably not as fine-tuned. So it's just going to see, it's going to see both of those signals as one signal, and it won't be able to recover the code.
That wasn't what I was concerned about, but I answered my own question. Because you can jam the second time, pick up the code, and then transmit the first one.
Yeah.
Cool.
Yeah.
That was what I was missing. Cool. Thank you.
Also with like car keys that do like complicated math on top of this. Say like you're in the coffee shop with your car keys, and well, this is for car keys that use like proximity, where you have in your pocket, you press the button on the door, and then it unlocks. Say you're in like a coffee shop with the keys in your pocket, and some guy's standing next to you, and he has a little device which is gonna communicate with your key and try to pretend it's a car. And then there's another guy by your car which has a device which is basically relaying the signals from your car to the other guy standing next to you, to your key. So the car is going to think that you're right next to the car even though you're not. You can do stuff like that. Mm-hmm. Yeah?
So earlier on you were talking about like the clock attack and like power attack.
Mhm.
How would you actually go about executing those?
You take a piece of hardware, open it up, figure out where the clock's coming from, and like tap into that signal, and then introduce those errors.
Okay, cool.
Yeah.
On that note, how do you time that kind of injection of the clock?
It's very dependent on what you're doing, but you're gonna have to figure out how, like, if you don't know anything about the hardware, it gets complicated. But say you know the program, but you don't know exactly which instruction it's on, you can try to measure power usage to try to see what instruction matches to a certain amount of power usage, and you can do stuff like that. Also, if the device does like output right before it does that thing that you want to skip, you can use that output as a trigger and then start introducing errors after that output has happened. Mm-hmm. Yeah?
And one of the previous hardware attacks you were talking about where you'd be able to skip instructions,
Mm-hmm.
say for like the password guessing. If you had the program set up in such a way that instead of on a on a correct guess, you would continue going through the code. On a correct guess, it would jump to some other part of code and execute the correct or
Yeah.
the true part of the instruction.
Mhm.
Would that kind of circumvent or prevent that type of attack?
No, because if you introduce the error on the comparison, you might cause the comparison to work wrong,
Okay.
and then you can use that effect to follow the correct code
Okay.
path. Yeah.
What do you see as far as the future of hardware security?
Future.
Do you see a positive trend in the security of our hardware, or is it?
Yes, because I believe like a few years ago, like replay attacks were like easy to do and common, and now it's getting harder. So stuff is getting better. Also stuff like hardware-based second factor authentication is becoming more common, which helps circumvent some software issues. But yeah, things seem to be getting better. Yeah.
So with Bluetooth, it's like two signals
Mhm.
syncing with each other and saying, okay, I'm at this device. So could you see a possibility where you can impersonate a Bluetooth device and send a certain signal and then mess with somebody else's hardware?
You can definitely do that.
Okay.
But there's like encryption behind it and stuff like that that can make it a little difficult. But it's possible. Yeah?
If you don't mind me adding on, someone who is a very prominent, leads a research group on radio frequency security, once said to me, the only safe way to pair a Bluetooth device is in a Faraday cage. The only way to do it. And this is by someone who is like a very prominent radio frequency researcher and runs a whole security team. It's no good. It's the extent of what I know about Bluetooth.
Yeah?
So if I, like, say I do want to do this stuff,
Mm-hmm.
like how much would it cost to get started?
So this device right here is about $32 on Amazon, and it comes with this antenna stuff. So it's pretty cheap to start listening. The transmitters are more expensive. I think the most common ones are like HackRF and Lime SDR, which are like about $200 to $300. Also, if you want to get into like the clock glitching and stuff, a useful tool are FPGAs, which are field programmable gate arrays, which it's basically like programmable hardware that you can reuse. Yeah.
How would they go about doing that legally and not get any of us in trouble?
Do it on devices you own and have permission to mess with. Mm-hmm.
Okay, so I heard this one thing a while ago, and I just want to see how legit this is. I heard that if you're just like sitting in a parking lot and you have your clicker thing, that you could just keep hitting the locked door, and it's like pretty likely that some other car in the parking lot can also be like, if you're holding down a lock, they could be trying to unlock the door and you're trying to like lock it.
Yes.
It's like, what's going on? Is
So
this true?
like this thing, if you hold it, it's just going to keep making that signal.
Mm.
And there's probably other garage door openers that operate near that frequency. So it's going to be making some signal, and someone's going to try to open their garage. But this is going to mess with that signal, so you can definitely do that.
How common is that? Like, how many are on the same range?
I don't know. Yeah. Mm-hmm.
If we're having Ask Thomas hardware myths idea time, can I throw one in?
Yes.
Okay, so I've definitely seen when people have like a clicker and then they put it to their head. That feels like turning your brain into a radio tower. Is that idea? Is there any science behind that at all?
Wait, so they put it to their head and it does what?
Theoretically, if you put it right here, your clicker right here, it will create some kind of amplification effect.
Well, that's
That's true?
That's true.
Why?
I don't know exactly what it is, but it's something about the shape of your skull, like reflects the It's basically like a parabolic reflector, kind of like you see on satellites. So
Oh, the back of your head is a parabolic reflector? Okay. Oh, no, this is bad.
I was checking to see if the amplitude would change of the wave, but nothing noticeable. Yeah. That might be because I'm like turned away from it.
You're not reflecting the waves with the back of your skull.
Yeah.
you gotta point the top of your head high.
Oh,
I was just pointing that way.
this is bad science.
Thomas, you need to keep the thing still and just move your head.
No, don't. This is terrible science. I'm sorry I brought this up. Never mind. All right, so now,
Yeah?
what hardware was Anna holding?
A toaster.
Oh, is that the toaster that got washed?
Yes.
I see.
What? Yes.
I see.